Another story at the same time. Another Nobel Prize. You see, Nobel Prizes are coming in every slide I am showing. This is crystallography. This is what you should enjoy. 2014 year of crystallography. So don't believe me, somebody says, what is there in crystallography? See, everything is there in crystallography. At least Nobel Prizes are there every year. So here is the Nobel Prize which was given. And here is a technique which is slightly different from standard crystallography technique because there is a use of DNA fiber in that crystals. This is fiber diffraction. So there can be always a quiz for the first year students here. Structure of DNA was determined as double helix, but there was no crystal. So far there is no crystal which has been grown to actually show this particular experiment for the success. You can get fragments of DNA, you can get nucleotides, nucleosides, several of them, oligonucleotides, and show that there is this double helix formed after this discovery. So this was a fantastic, super duper major discovery and a molecular life. At this stage, I must mention one which I have not shown here. There was a person by name G.N. Ramachandran. I don't know how many of you know G.N. Here in India. And he did a more complicated structure than this stupid structure. I'm sorry to use the word stupid. Because this is stupid in front of what structure he did, the structure of collagen. That was a triple helix. But unfortunately, collagen is not so important as DNA. So he lost out. It is around the same time he did this experiment. Not around the same time, not too far away. 1962, not too far away from here. But he did the triple helix. But this is what happens. G.N. Ramachandran got the highest crystallographic prize, the award prize. But I don't think he ever was able to get the Nobel Prize. But in my opinion, if there was one Indian so far who could have got a Nobel Prize, that is G.N. Ramachandran in India. He missed it out very narrowly, very, very narrowly. And the structure of a triple helix through fiber diffraction was much more complicated than double helix. You should remember that, just recollect. Remember, G.N. Ramachandran's contributions to crystallography has been enormous. Somebody told me the other day that G.N. Ramachandran is not a crystallographer. I was so very upset with that person, I told him you are an idiot. You have no idea whatsoever. And this happens to be one of the senior professors of the institute. He said he is a molecular biologist. I said, where is molecular biology without crystallography? Think about it. Molecular biology came after crystallography. Now molecular biologists jump up and down. Unless they see the structure, they don't know what the hell is going on in molecular biology. So structure, this forms the basis of it. And this is the thing, this is the advances. This is where crystallographers in India lost out. Definitely lost out. There are only a few fossils like me as crystallographers, the rest of them disappeared. We could have had a wonderful crystallography country here, but they all got fossilized because of this problem. Advances. One of the major disasters of this country is not to provide, until today, so much of money is wasted in everything, but they have not provided a proper synchrotron facility in the country. It's a pity because even a small nth-rate island somewhere has a synchrotron facility and we don't have it. We have to go there, go somewhere and collect the data. It's a pity, thousands and thousands of crores are wasted. But we were not given the synchrotron facility. Anyway, that's how crystallography lost out. So we have high-speed detectors, computers will go faster, and then the structure determination and data reduction, the phase problem in crystallography, the major problem, which is still an unsolved problem. There was a solution which was given to the phase problem, and that is something which allowed for the determination of the crystal, taking a Nobel Prize. Nobel Prize for every step in crystallography, every major step. Just getting the phases, getting the starting phases. So in tomorrow's class, I will do that for the students who came to the class today. I will do this part tomorrow, the Carr and Hoffman's Nobel Prize. Yeah. So that is where we enter the present. We are still to go to the future. I think I must be. And I apologize if I am taking too much time, but I try to hurry up and wind it up. Give me some extra time because I come very fast to the present. This I don't have to tell you because all of you know about it. Because this was a prime factor for us, even though Ricky himself told that I don't want to be called myself anything. Because he has been removed from the job, he has been thrown out of the place, he was treated so badly. He is a very personal, good friend of mine, so I can talk freely about him. Inside he is a real Indian. But he does not want to be called an Indian because of the way he was treated in India and put it out from India. in the early years. So this is the structure of ribosome. The structure function now molecular biology, real hardcore molecular biology comes up here. So because you do the structure, you are also coinciding that with the function. I don't think I'll go into the detail, but the first ribosome structure, in fact, was solved by IISER in 2000. And that was a real beginning of understanding of how ribosomes work in the system. And this is a very, very remarkably important discovery. And then, of course, the famous quasi-crystal, the deviation from symmetry. Nobody thought that this gentleman will get a Nobel Prize, because he was actually put out by the picture you had in the beginning of the talk, by the person who was holding apple in one hand and a helix in the other, none other than Linus Pauling. He said he has no sense, he has no idea of what he is doing. He is looking at a twin crystal and he is calling some nonsense as 5-fold symmetry being found and so on. There is a lot of story about it. I am sure you have heard, I was told you were writing about it. So you had this lecture, the Nobel lecture heard, so I don't want to go into the details, except to say that this is another Nobel Prize. You see, the basket of Nobel Prizes coming as I keep talking, and that is, this is for the discovery of quasi-crystals. Something about quasi-crystals which I thought I will mention, but since you have heard the talk, I think you have heard from the authority. I don't have to talk about it, right? Except to show you that there is one small issue which probably he never said to anybody, and that is he didn't do the X-ray diffraction. This is a secret. What he did was electron diffraction. So he looked at this part, this is the 5-membered part, the 5-fold symmetry part. He did electron diffraction, not X-ray diffraction. In fact, if X-ray diffraction he had done, you would think also that it is a twin crystal. I don't blame Linus Pauling fully on that issue, because it would have looked at, if he had looked at the X-ray diffraction, it would have looked like a twin crystal. So he did electron diffraction. No more detail on that, let's go faster. This is the picture. And then there is one other issue which is hanging around now in the present, which will have a future, that is the charge density approach. I will not have time to go into it, except to tell you that when you solve a structure, you treat the structure as though it is made up of hardcore billiard balls. The atoms are looking like billiard balls, but they are not. We know that when the bonding takes place, they have to get deformed. And these deformations can be mapped now very comfortably. And this is one of the recent deformation maps from one of our work. I thought in these slides let my small work also be shown to you. So, this is something where I can see there is a lot of excitement about fluorine. You know, if you go to Anshu's office, he's put a big poster saying some RVHF interactions, what is it, real? What is that? Some real is whether it is real or imaginary. Something he has put there. So fluorine is something which is, it's a very funny element. It is the most electronegative element in the periodic table. It has the same size of hydrogen, and so it should behave like hydrogen. But it is the most electronegative element. Then it is one of the halogens, so it should behave like a halogen. And most of the compounds with fluorine are very important in pharmaceutical industry. So all these things make fluorine a very interesting element. And there was a speculation always that fluorine cannot be polarized. So here is the first evidence of polarization associated with the fluorine. These are known as the deformation density plots, where you see that there is a little tongue which is coming up, and that tongue is interacting. In this case, there are two tongues coming out. They are interacting with the blue parts of the so-called electron density distribution. So there is a positive, negative kind of a electrostatic kind of interaction between a fluorine and a fluorine. It is an FF short interaction, and this has been quantified. And this kind of a work has a future. It's currently in full way vogue, and it will have a future. This is the last part of the talk. Beginnings of the future, I call it, and I call it as crystal gazing. See, one of the over 2 dozen Nobel Prizes since one quantum discovery. This is the past and the present. In the 2000 itself, if you look, from 2000 onwards, the 13 years now, 6 awards, 6 of the 24 awards have gone to crystallography. This is a big percentage. That means crystallography is on the up. It is just growing. It is very, very young. It's 100 years, but very young. It will grow. It has to grow because 2000 is a very good example. 2000 to 2013, 6 Nobel Prizes, so it has to flourish. It has to go forward. So it is just made a beginning, as a matter of fact. In fact, the most recent one is the G protein, which all of you have read about. There is another one, which is the so-called study of liquids. Now solids are over, we want to study liquids. These are liquids at room temperature, but we want to make them into solids by either application of low pressure, high pressures, or low temperatures. So we can make compounds of this, and this is the type of a work which in fact is initiated in IISER as well. So I don't want to go into the detail of it. But what I think is the future is to see reactivity. Here is an example which is just published. No, this is not yet published. This is unpublished result. This is just published in the form of a thesis. The thesis examination is next week. Okay, that's the latest result. When you see that, if you look at benzoyl chloride, you see that this is the type of electron density maps you will get. This is the electrostatic potential map of benzoyl chloride. The color code tells that these are the negative regions, red is the positive region, and green is the neutral region, and yellow is the somewhat neutral region. And you see that these are the positions where you now put fluorine derivatives. So you make a monofluoro, difluoro, trifluoro, tetrafluoro, and so on. As you see, the negative region which is coming out here, which is what we call as a sigma hole, is starting to develop depending upon the nature of the fluorine which is substituted, the number of fluorines which are substituted, irrespective of what is this structure. And what is also more interesting, I don't have time now, this, if you can imagine that this is the body of a tortoise, you see that it is starting to bend here and become a more mature tortoise. So if you have a tetrafluorobenzene, you see that this sigma hole associated with fluorine is enormously enhanced with the presence of other constituents. These are the compounds which have been, these are very simple compounds, and all these are liquids. So we see now chemical reactivity per se. We can visualize chemical reactivity based on substitution. So this is real hardcore chemistry we can do with crystallography. On liquid samples which are now cooled to low temperatures to become solid. This is the last part of the talk, which I will resolve crystallography. Obviously, crystallography has been a sort of a dull subject because it is all static. In the class we discussed that even the atoms which are moving will create errors, and what we plot as those beautiful thermal electrodes, they are actually error bars. What we call as thermal electrodes are error bars, because we cannot determine where the atom is. But now advances have been made in recent years with femtosecond and picosecond X-ray crystallography. This is the latest paper which has appeared on trans-cis isomerization pathway in photoactive yellow protein. I was thinking of spending a few minutes on this, but no, I will not. I will just finish up the talk by showing one more example, which is from Philip Copland's lab. This is an introduction to his visit here. So I'm sure you will enjoy his visit when he comes in January. So this is the femtosecond optical pump probe spectroscopy and picosecond X-ray diffraction technique. So we are combining spectroscopy with X-ray diffraction. And these X-ray diffraction techniques now are not going to use a single wavelength branch law condition. We are going to use Lawley conditions. So all wavelengths will be used, and these are all simulated patterns a priori to the diffraction pattern. So we have this structure. As this structure changes from in a femtosecond, we will measure the changes that are occurring. And we see here, these are the electron densities which are changing at the picosecond level. So we can go to those kind of challenge the spectroscopies at their time scale resolutions. And then, of course, the latest, the most recent. These are now reality. If you go to Stanford, you can see a hole going through Stanford and cutting across the river, which goes to the sea, and comes out from the seabed and back into the tank, and that is the X-ray free electron laser source. And so we have now X-ray lasers. So with this, we can not just do femtosecond crystallography, we can even attempt higher level resolutions on the time scale. So we can do some fantastic, successfully do X-rays to successfully diffract from individual molecules. So instead of looking at structures which are now collection of molecules in a box, all these box and symmetry and this and that, we can forget. We just take a molecule, shine X-ray laser on that one, and then see the structure. So that is the future. And this future is fantastic because we can see molecules And when we start seeing molecules, molecular biologists, watch out, we will start you to rethink about life. So we can start thinking about life once again. DNA is not the end of life. DNA is one of the molecules of life. So life is still, nothing is understood. And here we will see now with respect to time resolution. So we can not only see how the molecules are coming, we can also see the evolution of molecules. How the molecules could have evolved over time. So the entire thing will now become 3 question marks and 3 explanations in my opinion. Definitely tells you that there is a future for this area. And with this I will end my talk, thanking all my students who have helped me putting up these things together. And thank you very much. I'm sorry that I took a little longer than what I should have taken. 13 minutes long.
Are there any questions?
I have 2 quick comments.
Please.
Because of your time also said something. We talked about the patience of crystallographer. The author took 16 plus years to solve the structure
Yes.
by 11B12.
Right.
So she was not only patient but also very persistent. Second comment is that Linus Pauling actually got double yummy because he was not part of double helix as well as quasi-crystal.
Yes.
So 2 Nobel Prizes that he could be part of. That's why he told him that you are a useless fellow to his chairman
Yes.
that he should learn.
He should be removed from the, he lost his job. Don Shetland lost his job.
Right.
He used to even call him your quasi-scientist.
Yes.
So
In fact, I still remember, you know, Professor Ranga, who did some work in India. You know, Indians have always worked. You see, this is where I say that crystallographers have sort of, gone into the background. I'm happy you made the comment. Ranganathan and Chattopadhyay, Kamani and Chattopadhyay, did a lot of work in project